Thank you very much. It's my great pleasure to be here and attend such a methodological conference in a different building, not in our department. It gives us additional excuse to produce a little bit different talk, not only addressed to physicists. So at the very beginning, I will show you what I'm not going to discuss. This is one of the slides of my standard view graphs. I will not discuss it at all. I can produce such slides. This is, by the way, some complicated, interesting state, multi-party entanglement, but I will pose a much simpler question we never pose in our department. We never ask what is physics, because we presume we know what physics is. However, I was advised that here are some people at the audience who are not physicists, who are somehow eligible to pose such a question. So, look, okay, to be honest, I don't know what physics is, but I can give you an example. Here's my key. I just raise it and drop it. It fell down. I can repeat it again. What you will observe, it behaved similarly, but a little bit different. But basically, you see that the keys fall down. Now you can ask more concrete questions. Why they fall, how fast they fall, and we know the answer. Due to physics of Newton, we can compute the time of free fall from the height h. G is, of course, the gravity acceleration related to Earth. And then we can pose more precise questions and try to answer them, to predict the behavior of simple phenomenon which we can observe in our world. So basically what I always advise our students is to look outside. Here we have to make some, to look how the world looks like and to observe something interesting, a phenomenon, and try to understand it and maybe predict new one. So look, you can pose a question concerning those keys. What happens if those keys are smaller? Here you see smaller, very small. They will also fall down. You can now pose a question whether they will fall with the same speed. Yes, in a sense, and no. Why? Because, of course, if they are very small, then perhaps the role of air friction, which we somehow usually neglect, might become, thank you very much, more, important. So in a sense, I would claim that physics is an art of finding appropriate approximations. Look, it's really an interesting and nice word. Physicist is an artist, provided he's able to solve an interesting problem and find appropriate approximation which lead to nice solutions, which can be compared with experiment. So I will not claim that every physicist is an artist, but at least some of those are. In a sense, my another favorite example is like skiing. Not every skier will be an artist, especially those skiers who ski in the standard piste skiing usually are not. But if there is a skier who skis out of the piste and puts his tracks on the fresh snow, it could be also a kind of a special art. So let's see if it works now. Yes. So we know more or less, or have kind of impression, what physics might be. Now we want to tell something about quantum physics. Wow, what is quantum? So again, a simple answer would be a physics suitable to describe small objects on the scale of an atom. By the way, have you ever seen an atom? How big it is? Have you seen it? Never. Is it too small, yes? It's really small. Look, those of you who studied physics, you of course know, the typical atom like hydrogen is really small. P means picometer, is 0.5 times 10 to minus 10. So really it's not easy to imagine what means 10 to minus 10. Mathematicians do not care about such small numbers. It's almost like epsilon. Sometimes we need to care. By the way, there is also nucleus, even smaller, 10 to minus 15. To give you a kind of idea, I found the following comparison. You know, the population of Earth is about 7 in Polish milliards, in German also, in English billions, 0.77 times 10 to 10. So if one atom you can compare to 1 meter is almost like each of us to the global population. So you see, there are many people on our Earth, and the comparison atom to 1 meter is like each of us to the global population. Also, the age of universe is about 14 billion of years. So in a sense, we know what is 1 year of time. So the relation 1 year to the age of the universe is same as atom to 1 meter, more or less, which is quite a ratio. So we are taught now the word quantum refers to the fact we are taught about the atomic model of Bohr because the energy and momentum of, let's say, electron which moves around nucleus are quantized. Quantized, so they are in a sense discrete. You can find energies. Here's the axis of energy, and there is a ground state, energy of the ground state, there are excited states, and those energies are quantized. So in a sense, this word quantization refers to the fact that quantities do not take all possible values, but rather a discrete set of values. Of course, it's oversimplification, because here, in fact, I should refer rather to expectation value. So the average velocity or average position is quantized. Another argument that physics is quantum, since light, on one hand, reveals properties of a wave. You know what a wave is? Oh, here is already a wave plotted by Professor Spawek. And also it reveals nature of a particle. And this was also already flashed by Professor Spawek. We have photon energy, and then it's proportional to the frequency, and this proportionality constant h, or h bar, so h over 2 pi, serves as a kind of symbol of quantum theory. It's a famous Planck constant. By the way, in the standard units, joule times second, it's a really very small number, 10 to minus 34. So already 10 to minus 10 was a small number, and it is much, 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 much smaller. And then this number here appears in the famous relation of Heisenberg. Delta x times delta p is larger than something. Something is, by the way, exactly h over 2. And delta means the variance of experiments which is made by measuring, let's say, position or momentum, in general, coupled variables. By the way, a nice question concerning names. How do you think? Who wrote this formula first? Yes, point for you, yes, very well. Not Heisenberg. In a sense, it's interesting to see that the famous paper of Heisenberg, of course, the idea was his. It was written such a nice tilde in German, yes, so wave, by the way. It was proportional of order of h, and only in this very same year, in fact, this paper of Kennard appeared maybe half a year later, and I think in this very paper, this formula appeared here, so it's a little bit maybe unfair, so is the life, that not all of us know about Kennard, and the Heisenberg-asymptotic relation is now usually written like this. Thanks, Richard, point for you. So uncertainty relation asserts fundamental limit to the precision with which complementary variables like momentum and position can be known. And therefore, here's a key difference. Here the motion of keys are in some sense deterministic. Okay, of course here you don't know exactly what the reflection will be because of the shape, but you know exactly in a deterministic way how long this path will be traveled. Oh, this was in some sense also a bit stochastic component here. However, in general, classical mechanics is deterministic. I'm not talking about deterministic chaos here right now. However, the key difference is that quantum mechanics is different. It's probabilistic. It only can answer us the question, what is the probability that a given particle is registered here or there, or has a given velocity. It never can answer a question whether the particle is, for instance, here or there. Only gives us probability with which this particle can be registered. And then, look, this is again just slide for non-experts. Look, we try to understand quantum theory, quantum mechanics, and for last 100 of years, a few years ago, we celebrated 100 years of quantum theory. You know, more or less, we believe it was started with Planck lecture in 1900, so 2000, so 18 years ago, it was 100 years. And now it is taught all over the world. And amazingly, so many practical devices were invented, were found, and they work. We use them, not even knowing that they are based on quantum theory. So for instance, all the gadgets you have in your pockets, or somewhere here, like diode, electronics, computers, LED, stands for light-emitting diodes, liquid crystals, so your watches, cellular phones, like pens, so data carriers, and whatever. All of those devices are somehow based on the laws of quantum theory. So it's not only a kind of philosophical question whether we like quantum theory or not, but the people who are interested in technology, in, let's say, business, in practical applications, they really use quantum theory and basically cannot proceed without quantum effects. To make a short break, you see a picture here. What can you see? Two people. What they are doing? They are talking. Yeah, they are talking. I even can tell you who is presented here. It's Otto Nikodym on the left and Stefan Banach on the right, talking in Cracow Planting Garden, not far away from here, in the summer 1916. So it's almost exactly 100 years and two more. So we celebrated almost 2 years ago 100 years of this discussion. I will return to this story later. It was just a short break. And now I will introduce the simple object quantum state, or quantum wave function. So again, from the, sorry to say, but philosophical perspective, I would say that quantum state is just a mathematical tool. There might be different tools used, which allows us to compute probability of results which are measured. It's some tool. And of course, somebody can use one tool, maybe another person can use more sophisticated tool. The point is that the results should be correct. So if this function depends on position, it's sometimes called wave function, is a function of the variable x, and exactly it determines, so basically its absolute value square the probability of finding a particle at point x. For us, it will be interesting to return to this case and take a state which is element of the, well, Hilbert space, but in fact it's a vector. If you don't like the idea of Hilbert space or don't know nothing about it, don't worry. It's just a vector. So in a sense, look, this is a vector. You know, I returned from Italy, so it's like Italian vector. Okay, vector, oriented somehow. And it has only two. In the simplest case, this vector lives in two-dimensional space. Well, why in two-dimensional? In one, it would not be so interesting, because we assume that we discuss only vectors of length 1. So in one dimension, there are only two options, left or right. In two dimensions, you can somehow rotate this vector wherever you wish. And then it will be easier for us to use complex numbers. And now we can use bases 0 and 1. This is like orthogonal bases in this vector space. And our coefficients C0, C0 are just complex numbers. So it describes state of a system which classically has two distinguished positions. Let's say this red points up or down. Or if you have a coin, heads or tails. And then we assume that this state is normalized, so the length of this vector is 1, which means that the coefficients C0 and C0 satisfy the following relation. They are complex numbers by their absolute squares. Sum of them is equal to 1. and those squares correspond just to probability that you will register state 0 or 1. And then it's easy to see that all possible states of such a system are equivalent to different orientations of this vector, which sometimes in our jargon we call spin. We call it spin 1/2. And then the space of all those states is somehow referred to as Bloch sphere. It's just standard sphere, so mathematically S2 embedded in R3. So standard sphere, let's say of length 1 or 1/2. In other words, classically we have only 2 points, up or down, or 0 or 1. Quantum mechanically, what we do, we use, I think, an important simple word. Would you like to guess which word I now refer to? It starts with letter E. Yes, in English, yes, to embed. We'll embed those 2 points inside larger dimensional space, now not Hilbert space. To show how it works, I will make a following, again, experiment. It's not Gedanken experiment, it's practical. Oops, sorry. So you see it's practical because it should be a sphere. But it's not a sphere, you see, the physics is, like, it should, but you can imagine it's a sphere, yes? So it should be a sphere, it's not. And what I have done, I have embedded those 2 points, 0 and 1. 0 is here, 1 is here. So you see, the set of classical points, well, you can imagine it should be, another effect, yes. Sorry, it was not real, okay. You see, in physics experiments could go well or not very well. I wanted to show you in a second decoherence. But this is very fast decoherence. What happened now? The set of quantum states immediately reduced to the set of classical states. And I didn't want it, but it happens. It also happens in the real life in the quantum physics. Sometimes you really want to have a state. By the way, this state is called coherent superposition of 0 and 1. And we like this state very much. You obtained it by rotating this state, let's say 90 degrees. And with respect to this basis, we assume that this basis is chosen. It's chosen by interaction with some environment. So with respect to fixed basis, this state is, let's say, maximally coherent. And then decoherence means that those states, due to interaction with environment, they tend to the classical state, which is only 0 or 1, or probabilistic mixture, which corresponds to any point from up to down at this axis. So those states, quantum states 0 and 1, they are classical. They correspond to standard coin up and down. Those states here, all other states from the Bloch sphere, blue sphere, are, let's say, non-classical. But those plus and minus, they are just combinations or superpositions of 0 and 1 with sign plus or minus. They are the most coherent as they can be. So quantum superposition is a kind of quantum effect. It's a pure state which differs from a classical mixture of quantum states. So classical mixture is here exactly at this line joining 0 and 1. So at this stick. And quantum states are just outside this stick. But as you have seen, due to decoherence, the lifetime of such a state is relatively short. Here it was even too short. So, in classical world, if you discuss in theory of information, one works with bits. So 0, 1, 1, 0, you have many bits, up, down, up, down. And of course, you know, you can use different gates, nends, and all numbers can be written in bits, and all operations can be somehow described in classical bits. And then there is a theory of quantum information, but instead of bits, we have qubits. So here is one Bloch sphere and orientation of vector like this. Here's another one, and all of them are described by wave functions or elements of this auxiliary mathematical space. So what are advantages? There is a larger space of states allowed. I recall, classically are only 0 and 1, and quantum mechanically are, for instance, arbitrary orientations of the spin. And also larger set of operations, because classically you can only negate 0, change 0 into 1, and quantum mechanically you can have arbitrary you can rotate it in an arbitrary way and get, let's say, square root of naught. You know what is a NOT gate. It changes 0 into 1. Classically, there's nothing like square root of 1. And quantum mechanically, of course, it is. You just take 0 and put it to the equator. I should finish at quarter past. Okay. Thank you. So we know already what is a superposition of two states. Now if I have bipartite system, like 2 spins or 2 bits, so one can point up, one down, and you can have, again, superposition, coherent superposition of bipartite state. For instance, such a state like 0, 0, it means state with 2 spins up are superposed with states with 2 spins down. And this state, again, in our technical notation, we put it like 0, 0 plus 1, 1. It is very strange state. It's non-classical state. Look, can you imagine I show you 2 coins, and then I give you 1 coin, I toss it many times, and you see that with probability 50%, it is head or tail. Then another coin is exactly like this. And then I toss 2 coins in the same time, and I claim that if I see on one hand heads, it implies that it must be head on the other coin. Will you believe it is true? You would think it's not possible. I'm cheating. So classically, you believe such states cannot exist. And quantum mechanically, they do. So,
this is possible in single basis.
Sorry?
In single basis, this is possible.
Yes. In short, a state, if we have bipartite systems, we define states which are classical or non-correlated. They are called product states. So this notion here mathematically is called tensor product. But basically it means that one spin is here, one there. There is no correlation whatever. You can just rotate one object and the second object is not correlated with it. This is the most classical situation we are used to. And all other states which are not of this kind, they are not of the product form, they are called entangled. And now this state called Bell state is somehow one can show it's as much entangled as it might be because those correlations between both results of both experiments with both subsystems are the largest, the strongest. So in short, entanglement on one hand is also a superposition, but no superposition for bipartite or multipartite systems. And then entanglement in short is an effect, quantum effect, which relies on non-classical correlations. I put this cat into the title, Schrödinger cat. Okay, it looks like this more or less. I'm sorry I forgot to quote the author of this picture. So this story, you might know, the story, of course, this is really a Gedanken experiment of Schrödinger, that there is a, rather complicated device. Here is a nucleus which may go apart or not, may emit light, and then there is a special device and the hammer which may kill the poison, and this poison may evaporate and immediately kill the cat or not. And then, if you don't look at it, you don't know what is the state of the cat, whether he's alive or not. So the story says that this nucleus has not emitted poison, was not spilled yet, and the cat is alive, or just the opposite. The hammer already struck this glass, poison is there, and cat is dead. So as you see, this is nothing else as a special kind of entangled state. And then you can interpret it in many different ways. So of course, it used to be a kind of Gedanken experiment, but recently, in the lab, people can, in some sense, create such a coherent state, so such a cat state. So here's a result of famous experiment of Arosh from 2008. What you see here is a probability distribution, and then great means large probability, and so here is kind of probability goes up, and those 2 peaks, they mean that probability is here or there, and then this is an evidence, then an experiment you can create. Okay, of course not cats, but people work with photons and atoms, but still you can, in experiment, realize such a non-classical superposition of bipartite or multipartite states. So here's a nice joke about your cat, Mr. Schrödinger. I have good news and bad news. Okay, if he is a little bit alive, a little bit dead, so maybe the news is also like this. So I recall only from my studies of Polish poetry, I have to switch into Polish. I like always to quote Koziołek Matołek, so it goes like, jak nie umrze, to żyć będzie. Tak lekarze powiedzieli, which is not exactly the same, but almost. And then, as I already referred to skiing, is another nice joke. Interference somehow allows in quantum theory to interfere such strange two paths. Of course, as you can guess, classic, I was skiing a lot in my life. I haven't seen such a picture so far. Maybe I'm not skiing enough, but it's not easy to see such a object. By the way, I was trying once to produce such a, especially such traces, but nobody was observing. No, but I was going up, so I went like this. I was making special tricks to do it, but I'm not sure whether ever observed and appreciated this fact. So look, concerning entanglement states, I know there are here experts in the audience. I'm a bit ashamed of showing such things, not knowing much about it. But we already discussed Bloch sphere, and then in classical optics or classical physics, the sphere, okay, mathematically is standard sphere, but in optics it's sometimes called Poincaré sphere. It describes polarization of light, and you can have, which is called circular polarization, left or right. So here R stands for right, L for left, and here is the linear polarization, let's say V like vertical, H like horizontal, and here are combinations, like diagonal, anti-diagonal. So any state of light, polarized state of light, corresponds to the point on this sphere. And then there is another interesting effect, which is related to nonlinear optics. If a blue photon, by the way, here color is important, blue, because it has larger energy. It has large energy, it can, interacting with this nonlinear crystal, it can produce a pair of two red, so less energetic photons. So there are two of them. And then now this picture, I'm sorry, those colors here, they are related to energy. Those colors here are now related to polarization. It's nothing to do with energy. So basically this is, those colors here correspond to polarization of light produced out of this nonlinear crystal. And then you can get an entangled state that there is a one photon is polarized horizontally, second vertically, or just the opposite. And then this effect was observed, created, and measured also kind of a decade ago. So quantum entanglement is a non-classical effect. It shows certain quantum correlations between the results measured by two detectors. So we have here this blue photon. It goes into two parts, and then you measure on one hand side something, and it's strange. You can predict results measured in the other lab. So this is really an analogy to this Schrödinger cat. However, there is no, it's important, it has no contradiction to general relativity. You cannot transmit information faster than light. So there's no, it's important to understand, we could somehow learn measuring, performing quantum measurement in part A. We will know what the observer in part B will get, but we cannot transmit information faster than light. And then entangled states do exist, but they are fragile. What means fragile? They can be destroyed due to interaction with an environment. I already observed, you observe here, so I wanted to show it in a more slow way. So exactly this is the point. So if you embed the set of classical states into quantum states and do nothing, what happens with the air? Balloon, air will go out of balloon, so it means that the set of quantum states will slowly evolve into set of classical states. So it's not so easy to work with those states in practice. However, this was just the model of decoherence I already produced with the balloon. So decoherence, in fact, it means that the quantum states, due to interaction with environment, they are projected back to the set of classical states, which in this case is just the 2 points, 2 pure states, and the convex combination, so the mixture of those 2 points. So if we consider closed quantum systems, situation is simple. The evolution is unitary. So U is a unitary operator, which basically means it preserves unity, it preserves length. It's kind of isometry. It's only rotation, nothing else. It's very simple. And then this operation is linear, deterministic, and reversible. This is simple, and it would be simple if we could shield the quantum state from environment, if we could really have an isolated quantum system. But we cannot. I've never seen, and nobody has ever seen, any small system which is isolated. Perhaps universe as a whole is isolated. Okay, it's a kind of a matter of taste. But all small systems we deal with in practice, they are not isolated. And then if you have an interacting system, so if you allow for a measurement or interaction with environment, then the evolution is not unitary. In our language, it is unitary if you consider the both systems, system and environment, is unitary. But if you consider only principal system, you have to take what we call partial trace, so average over environment, and you get from this non-unitary evolution, which is non-linear, non-deterministic, and irreversible. So the paradox of quantum measurement is that to infer something about the quantum system, we have to perform measurements. And those measurements, in short, they change the system, they influence the system. So decoherence is irreversible, and then this is kind of a bad news. However, to generate such a coherent state, so I recall this state here is a coherent state, the effect of blowing a balloon is not a physical process. Physical is just shrinking of the balloon. What I would like to do, but I cannot because the balloon, I have only one, it's my fault. Okay, I can try. So this is a model of not physical process. We cannot do such a thing. What we can do to get this state here, much simpler, we can just rotate. Unitary evolution is allowed, so we can rotate this state to have it here, and then it will already be a superposition, and if we wait long enough, it will go back and become classical. But then you can ask, so what is a coherification? There is a paper written by Stanisław Czachurski and our other colleague Staszek is here, published this year. Coherification could be asking for pre-images. Decoherence is irreversible. You can always ask a classical state, where it came from. Moreover, you can ask, what is the whole set of possible states which can decohere? For instance, if you take this point here, those states here, all of those states which are at a parallel, certain parallel, they could decohere to this classical state. So what people study is just how to possibly diminish meaning or consequences of decoherence. And then if, for instance, there are some special conditions like low temperature or vacuum, so the chance for interaction of your system with environment is smaller, or there are some nice idea, decoherence-free subspaces. So there is an interaction with environment, but some subspaces of this space do not suffer this decoherence. Then the quantum effects of quantum information can live longer, and people try to find out nice models and possibly realize them in experiment, how to protect those entangled states, how to allow them to live longer. But as you see with this balloon, which is a nice example, very often they live very short. Here, Wojciech Żurek was already mentioned today by Professor Spałek. So I plot here, I took the liberty to show his important picture from his article in Physics Today in 1991. So you can see here is a kind of a border, quantum classical border. Classical part is well defined, and you see there's a very nice, booth of a soldier standing here. On the other side, in quantum, we see here Schrödinger cats dead or alive, and all those parts are not so well defined. Why? Because this is the key paradox. If we want to see what is on the other side, we have somehow to interact with those cats or with those objects, and then we would somehow interfere with them. Therefore, our knowledge of this part is kind of fuzzy and not precise. Moreover, this border here, of course, is a joke. It's not like this, there is a really border like between Poland and Slovakia. Fortunately, this border between Poland and Slovakia is already more fuzzy than it used to be 50 years ago. Because really, 40 years ago, if you cross the border, you could really see that you cross it because somebody will ask you for documents or fine. And now it's nicer. So in a sense, I like the fact that now those border between Poland and some neighboring states, not all of them, are already similar to this one, which is not so well defined. And then quantum information processing makes use just on those quantum effects, on this superposition state for one subsystem, or entangled state for two or more subsystems. So here is this famous Bell state. And this slide I wanted not to discuss. There are much more complicated states of many particles. And for all possible applications like teleportation, computing, quantum cryptography, such quantum states are used. I think I should slowly close, so I will allow myself to skip some parts on quantum teleportation. I was thinking there's enough time, but maybe you know the story, so I will just maybe just sketch. The idea is to teleport. Okay, what is teleportation? We want to take, for instance, your object and put it somewhere there, yes? No way. Yes, but if it would be a quantum bit, we wanted to take the quantum bit from you and let's teleport it to colleague over there. Is it possible? That's better. But it's still not possible. You can always say it's not possible. However, it only then could be possible if you have some additional resources. For instance, just this set of maximally entangled Bell states. So the idea is that Alice would like to teleport quantum states from A to B, and then it's possible. In general, it's not possible. It's only then possible if they share such a maximally entangled state of Bell. And then there are 6 people who wrote this paper, which is almost 25 years ago. And I think this paper, maybe my colleagues will agree, marked somehow really it was a great step in the theory of quantum information. So it was then realized by Schrödinger a few years later with photons, and then recently also realized in Spain, in the islands. From 2 islands were split by more than 140 kilometers from La Palma to Tenerife, and it works somehow. So I think I will slowly go to conclusion. I will not discuss a nice question I'm working on, which state is the most entangled. This is simple for 2 qubits, it's Bell state. For 2 Q3, it's also simple. However, there is mathematics which is based on Schmidt decomposition. I will not discuss it. However, already if you have 3 qubits, it's more complicated. Then the answer is still known. It's something called GHZ states. We have now 3 objects, and this is a very nice generalization of Bell state, 0, 0, 0, plus 1, 1, 1. But already if you have more qubits or qubits, the question is much more complicated. So here I allow myself to show you this picture. So this is a picture which is related to famous Borromean rings. They have this property: if you cut one of those, let's say the blue one, then 2 others will fall apart. And then this is a kind of symbol of those states, because if you perform a measurement on one state, 2 others are not entangled anymore. So there's a very fancy, special form of entanglement that if one ring is broken, so one subsystem is measured, 2 others are not entangled anymore. And we go back to the story of Cracow. So I know that there are some guests here who have not been maybe in Cracow before. So I will then show you a picture. So this is a picture of our Wawel Castle. If you haven't seen it, please go and see it. But I decided to show you this very picture to formulate a theorem. Yeah, it's possible to show a picture and formulate a theorem. This is theorem of my friends Danuta and Krzysztof Ciesielscy. It goes like this. With probability 1 minus epsilon, the bench Stefan Banach talked to Otto Nikodym in 1916 was localized in the eta neighborhood of the red arrow. So you see it's a very precise statement. However, they still work on functional dependence, E epsilon of eta, which is unknown. Sorry? Yeah, this is the question, exactly. They're still working on it. However, why this is important? Because they were talking, we know now about what they were talking about the Lebesgue integral, and then the Steinhaus was passing by. But look, try to imagine. It was 1916, middle of the First World War. Cracow was almost close to the front, so the Russians were already expelled, but still, it was not a good place to do mathematics. So Steinhaus was the only, somehow, professional mathematician, and then Nikodym and Banach, Banach broke his studies in Lwów and returned to Cracow. And Steinhaus was so much enthusiastic and amazed that they are talking about such advanced things. He introduced himself, then talked about mathematics, and from this very discussion, the famous Polish School of Mathematics was born. So here is a short table memorizing this discussion. There's a longer part in Polish, shorter in English. I will read here for you. Otto Nikodym and Stefan Banach in conversation about mathematics. This bench memorizes their famous meeting with Hugo Steinhaus in the planted garden in summer 1916. So last general remark, many years ago as I started to work on this field, somehow it was really only a theoretical field. And now for the last 10 years we witness a huge changes. Now the key question is, you maybe have heard about quantum supremacy. The idea is that whether we will ever, maybe soon, see that something which, like quantum computer, uses quantum mechanics, can compute for us something which is not doable or hardly doable classically. It's still not yet this point, but maybe such quantum supremacy will be achieved in coming years. And then really quantum theory is now already very much coupled, let's say entangled to technology, much more than it used to be. So in concluding remarks are simple. Quantum theory predicts existence of very strange states. Strange because they show non-classical correlations. For instance, superpositions and entangled states. And they can be constructed in experiments. They were constructed and used many times. And even though they are very fragile, because this decoherence happens, so you have to protect them from interaction with environment. But what means environment? Everything. If you watch at them, if they interact with some thermal field, it is killing for them. So even though they are fragile, it's possible to use them for various tasks in quantum information processing. By the way, you see immediately, you cannot be lazy in this quantum information. You cannot wait, let's say, weeks long and think what to do, because all those processes have to be performed relatively fast so that entangled states will not decay. So you have to be faster than decoherence. So one thing is you have to think how to do your operations, manipulations relatively fast, and second, how to protect the coherence from decoherence, from destroying effect of the outside world. So now we can witness practical implementations of quantum technology, and there are still many open questions. So I will somehow finish with a statement that everybody is welcome to contribute. There are many interesting questions we can pose and study, and then I'm pleased that there are so many distinguished colleagues here. So you see, it's very pleasant to see that something can be done, for instance, in our country. So I can, if you don't know, tell you that in, for instance, Gdańsk, Warsaw, Łódź, also Wrocław, Katowice, there are many clever people who work on those subjects, and the achievements are really appreciated in the world, what's very nice. So I'm very pleased that if I go to conferences worldwide, it's very likely that some results of Polish physicists will be quoted. So, returning to the first story, this is the bench. Bench memorizing the discussion between Nikodym and Banach. The discussion took place in 1916. The bench was opened in 2016, exactly 100 years later. It's located in the planted garden, very close to Wawel. If you have never seen it, you can go there, take a photo, or maybe better sit here and listen what they have to say. Thank you very much. And we'll also show that this last picture was appreciated by the math community. Maybe you know Mathematical Intelligence is a very, very appreciated journal, and this picture made it to the cover story.
Thank you very much. So do we have any questions?
In one place of your talk, you show us Poincaré's field.
Yes, which is the same as Bloch's field.
Is that homology sphere?
Sorry? It's the same.
Is the homology
Yes, so by the way, mathematicians claim there's only one sphere, and they are somehow do not understand why physicists use difference. Bloch, Poincaré, Stokes, okay, it could be also Stokes sphere. For mathematicians, there's only one sphere. And of course, for us, it depends on the context. Our spheres are contextual.
Okay.
It's the same sphere.
But this is the Riemann sphere.
Oh, yeah, by the way, it's another, yes, of radius 1.
Okay.
So it means it's sphere in one dimension.
No, sorry, no. This is standard sphere S2 in 3 dimensions. Yeah. Standard sphere.
I have a physics question. So what do you think about Penrose's idea that all particles are subject to decoherence because of the gravitational field?
Yeah. By the way, I forgot to tell you. I, on purpose, started with this key and I let it drop. To show that gravitation is crucial in what sense? Some of us, maybe I don't, claim they do understand quantum mechanics to some extent. But I believe nobody really understands how to combine quantum theory with gravity. And there are many people, clever people, who try to think of different kinds of quantum gravity, but still, this theory is, it's fair to say, it's still not satisfactory. So basically, nobody knows. But it's a very good question, of course.
Thank you. All right, let's thank the speaker again. Oh, sorry, there's one more question. Okay, last question.
Actually, just a comment that it's not quantum gravity, but for example, the gravitational field has a contribution to the gyromagnetic factor of the muon.
Yes.
Just I wanted to note that you mentioned that you also asked that the gravitational field is interacting.
Okay.
So
this is,
we can get some classical interactions also.
Okay, I agree. So there are two different somehow planes, and which one can make such questions, but still, quantum gravity is,
Okay, so let's thank the speaker again, and then, And now we have a